In the last video, number 150, we looked at an old SOA sample exam problem about Macaulay duration. And I was looking through that exam some more and saw some other good problems about Macaulay duration that involve things other than bonds, some other kinds of cash flows. And I do want to eventually go to those problems and look at those. But I thought it'd be good to go back to Broverman's book and look at 7.1.6 and once more at least look at a problem involving the Macaulay duration of bonds. It's kind of a specialized problem. It's kind of a tricky problem, kind of nasty as far as the calculations go. Got to be really careful not to make mistakes. But it does involve yet one more way to look at the formula for the Macaulay duration that I think is definitely going to be worthwhile. So the goal of the problem is to find the value of a portfolio where you've got two bonds and the cash flows are being combined. When you're given some information, you're given their Macaulay durations, you're given their prices per 100 of face amount, but not the prices themselves. That's important. The sum of their face amounts, and you're also told the Macaulay duration of the portfolio itself. So under current market conditions, bond 1 has a price that's per 100 of face amount of 88.35. What does that mean? It means it's 88.35% of its face value, and a Macaulay duration of 12.7. Bond 2 has a price per 100 of face amount of 130.49% of its face value, and a Macaulay duration of 14.6. A portfolio is created with a combination of these two bonds. Again, you have face amount F1 of bond 1 and face amount F2 of bond 2, and you're told that the sum of these two face values is 100, and the Macaulay duration of the entire portfolio is 13.5. The goal is to find the portfolio value, and if you think about that carefully, you realize value is basically synonymous with price. What is the price you would pay for this portfolio at time 0? Okay, maybe it doesn't seem like it's too hard, but I thought in solving this problem that it was pretty tricky. So you got to be careful. Let's go ahead and write down some symbols. Let's say P1 is the price or value of bond 1. P2 is the price or value of bond 2. The goal sounds simple. Just find the sum P1 plus P2. It's probably also worth writing down what we are given. We're given that P1 is 88.35% of F1. In other words, it's 0.8835 times F1. P2 is 130.49% of F2, 1.3049 times F2. Given F1 plus F2 is 100, and finally we are also given those Macaulay durations that you see. We are given that the Macaulay duration of bond 1 is 12.7, of bond 2 is 14.6, and of the combination portfolio is 13.5. All right, let's go ahead and write down the formula for Macaulay duration again. Dmac of J. It's a fraction, it's a ratio, where the numerator is the sum, t goes from 1 to n, of t times kt, where the cash flow kt is assumed to occur at time t, discounted back to time 0 with yield rate j, 1 plus j to the negative t, all divided by the sum, t goes from 1 to n, of kt itself, times 1 plus j to the negative t. Okay, and as we've seen in recent videos, this denominator is really the same as the price of the bond. This is the price or value. Okay, this equation, of course, could be rewritten by multiplying both sides by that price. Let me go ahead and do that and say that it's equivalent to saying the Macaulay duration, which I'll just denote by D, times the price equals the summation that you see. And that summation that's in the numerator of that fraction, well, if you've taken some physics or engineering courses, you might recognize it as a sum of locations times some quantities that you could think of as being point masses, if you like. Do you have to do this? Do you have to think of it that way? No, you don't. But I think it's going to be helpful, especially if you've had some physics or engineering and are used to thinking of it this way. This summation could be thought of as what's called the moment of the point masses that are the monetary amounts, the discounted monetary amounts, k1, 1 plus j to the negative 1, k2, 1 plus j to the negative 2, all through kn times 1 plus j to the negative n. With respect to the origin, with respect to 0, these masses are at positions 1 through n. Okay? Just could be a helpful way to think about this, to remember this equation, and possibly to visualize something. You don't have to think of it this way to solve the problem, but you could. It might be helpful. And maybe even because of that, give this thing a name, this summation, call it, say, capital M. Another nice reason for doing this is that now when we take the cash flows from both bonds and combine them into a combined cash flow, it's kind of like combining all the masses in their respective locations. And the moment of the portfolio is going to be the sum of the moments of each individual bond. Okay, and that'll be helpful for solving the problem. All right, so now we need to actually do the solving. And again, so this is the main new thing to think about. This solving is going to be a bit of a pain. The numbers are not pleasant to deal with, but we can do it. What we're ultimately going to do is, to solve for P1 plus P2, is first find F1 and F2, then use these equations to find P1 and P2, and then add them. And to find F1 and F2, we're going to use a system of equations, linear equations, one of which is going to be this thing, which of course is equivalent to, for example, F2 is 100 minus F1. And we need a second linear equation involving F1 and F2 if we're going to solve that system. So the bulk of the work is finding the second equation and also then solving the resulting system with some kind of messy numbers. Okay? So that's the main idea. If that's enough for you, you could probably stop the video right now. But if you want to see me finish the video, you can watch, or you could skip ahead to the end to see what the answer is, and you could try it on your own and check it. Let's think about the moments here. The moment for the cash flow from bond 1 is its duration, it's an M there, 12.7 times its price, P1. The moment for the cash flow that comes from bond 2 is its duration, 14.6 times its price, P2. And of course, I can replace P1 with this. So this is 12.7 times 0.8835 F1. And then P2 gets replaced with 1.3049 times F2. And then let's go ahead and simplify it. So 12.7 times 0.8835 gives you 11.22045 times F1, and then 14.6 times 1.3049 gives you 19.05154, and that gets multiplied times F2. And the sum, M1 plus M2, is the moment of the portfolio, and it has duration 13.5. So it's 13.5 times the price of the portfolio, which is the thing we want to find, P1 plus P2. And then we can go ahead and once again replace P1 with 0.8835 F1 plus 1 point, and then P2 with 1.3049 F2, and we can multiply the 13.5 through the parentheses and set this equal to the sum of these two things, and that's your second linear equation. Okay? Maybe now you want to stop the video and just jump to the end and try to solve it on your own before you go there. Let's go ahead and do more multiplications here. So we have 13.5 times 0.8835. So this gives 11.92725 F1 plus, we've got 13.5 times 1.3049 gives 17.61615 F2. This will equal the sum of these two things. Now let me also go ahead and replace the F2s with 100 minus F1. So that gives what? 11.92725 F1 plus 17.61615 times 100 minus F1, looking at this thing here, equals the sum of these two things with, once again, F2 replaced by 100 minus F1. And now it's just a matter of simplifying this crazy thing and solving for F1. More calculator work. So let's see, we'll have the constant term over here would be 17.61615 times 100. That'll give us 1,761.615. And then the term involving F1 will be, have this coefficient minus that coefficient because the minus sign there. So we can take the 17.6165 on the calculator here and negate it and add 11.92725 minus 17.61. I messed it up again here. Oh, I guess that's right. 17.61. Oh, let me try again. Sorry. 11.92725 minus 17.61615 minus 5.6889 F1 equals, the constant term here is going to be this thing times 100, 1,905.154, and then the F1 coefficient will be 11.22045, looking right there, minus 19.05154, 7.83109 times F1. Let's add that to both sides. So I'll negate this and subtract 5.6889. Gives 2.14219 F1. I'll have to divide by that, so I'll store that in register 0. Take 1905 minus this now, 1905.154 minus 1761.615. It's 143.539. We're almost done here, getting close. Divide by the 2.1414219, which is in register 0. F1, oh boy, F1 is 67. I'm going to carry more decimal places, 0.005727778. I'll store that in register 1. F2 is, of course, 100 minus that. Put a negative sign, add 100. F2 is 32.994272222 if you want to write stuff down. I'll store that in register 2. That gets, now we're almost done here, multiplied by 1.3049. That's P2, 43.05 approximately. I'll store that in register 5, which is above the 2. That's why I did that. And then take what's in register 1 and multiply it times 0.8835. That's P1, 59.20 when you round it. Add that to what's in register 5 and we should be done. Yep, that's the correct answer. P1 plus P2 if you round to the nearest hundredth is 102.25. And that is correct. That's the combined price of the portfolio, the combined value. 102.25. Have a good day.